Okay then, welcome to another one. Number 20. Just wait for the stream to catch up. Welcome to number 20. See if we're a bit early, at 48 minutes early. We got audio. Welcome to another. We've got audio. Welcome. Let's switch me back, switch me in. Welcome. Let's switch me out. So welcome to Hex Cobweb 20. Hustler 5. BTV ground plane. Think tank ideas. So, here we go. Drop me in. Give you a big one. How do? Welcome. It's been a while. And we're back here again. Hopefully it's not going to be too long, this one. Maybe. Okay. So, anyway. Hex Cobweb. What is a Hex Cobweb? I don't know. It's a combination between a hex beam and a cobweb antenna and a ground plane and an experimental stroke / anything else in between. Yeah. Hustler 5 BTV ground plane. When I say ground plane, I want some ideas for a ground plane. It's an antenna that can be used for a ground plane. Think tank ideas. Think tank and ideas. So we're inviting ideas today. It's gonna. I've got a few ideas I want to put past. Don't know. Maybe ChatGPT will have some ideas as well. I don't know. Anyway, so. Welcome. This is where we ended off last stream on Hex Cobweb 19. We've incorporated it as a ground plane. I haven't yet. haven't yet done it. The weather's been bad. So anyway, but what I've got some ideas of. Connecting up these ground planes, switchable. So I reckon this ground plane here, this will be the 4 meter band. Okay. Then you got your 6 meter band, the green. Then your blue will be 10 meters. Then you got your 12 meter band. 15 meter band and 20 meter band. Okay, now what I was thinking, you only, it naturally finds the right length, resonant length for the element and the band you're on, the frequency you're on. So it'll automatically go down the right wire, basically. So what happens if, once you get to the outer one, you was to switch in, so you break the connection and switch it down one of the others. Now there must be a combination here of switching in wires that would give you a 40 meter band and an 80 meter band. So instead of coming from here, might be better to go to the model. I'll tell you what, let's go to the model. Maybe you can see this. You can see this at the minute. So your 40 meter band starts from the feed point, goes round here, all the way around, and then back round to the feed point, to the braid and the inner of the coax. Now what happens if we was to switch it? instead of it finishing at here, there, we just switch it down this one and all the way back and switch it there or take it back. So basically, whatever band you're on, so let's try to work it out. Let's try to work it out. Say if this was tuned, this is going to be pre-tuned for 20 meters. Now for 40 meters we need to add another. We know this one is the 15 meter band, so we could use the 15 meter band, and we need to add a more length, another 5 meters basically. So we've got 4 meters down here and 6 meters. So could we possibly feed this round there and get the 40 meter band? Should be able to. It's all about the length at the end of the day. So you've got your 20 meter band flowing into, you'd lose a bit here. So if you used to switch it there and there, you'd lose this length here. So you've got your 20 meters, and we need to switch in. What's the next one? We've got this 50. Oh, there is a 17 meter band, isn't there? No, that's 17 megahertz, sorry. So 15 meters. So you could switch any combination. So basically we need some kind of switching system that need. If we use relays, double throw, double pole relay for each band, I'd have to have a quite complicated board. It'll be a bit like making an automatic tuner, but instead of using coils and loaded capacitance, we're switching different lengths in. So it'll be experimental, but we'll be able to measure it with our nano VNA. So what we need is the ability to switch any band with any other band, and possibly with. So you go round, you go start from here, you go round, and you go round on the purple bands, and then back round this one, and around this one, and switching around there. And somehow these bands, they're going to add up to maybe 80 meters. It's going to be experimental, but so I think we use a 1-to-1 balun. We've got the choke there, and we need a way to switch. So if you use a double pole, double throw, you could switch this one in and that one from one coil of one relay, and so on and so forth. So you'll always need to switch different bands on and off. So you'll have to start with a small band and switch up. But then you've also got whether you go quarter wave or half wave or 5/8 wave. So there's more to it. So ideally we'd be able to switch any combination of this lot here. So let's just say 1, 2, 3, 4, 5, 6 bands. So 6 is 36. What was I doing the other day that was 6? Oh, yeah. So I needed 36 of these stays. Let's go over to the model. Let's go over to the model now. So I'll disappear me. And I'll go over to the model. Right, we're down in the model. So let's have a quick look in the centre of the model. Oh, tell you what, let's switch me on. There we go. Right, so we want to go to the centre of the model. So we're in the centre of the model. We've got our bands, coloured bands. So this is going to be our 4 metre band. If I can get it to scroll over there, that's it. So we start from the feed point, go around. So we've got to be able to switch this one, disconnect. We need to keep that connected. So we'd have to start off. This would never need to be switched. Maybe. Yeah, it might need to switch it in and out. You always want to end up with something switched in, a default one that's switched in, or maybe not. So we go around there. And instead of feeding straight back, it then feeds to the next one. So I need to be able to switch. So we could change the design somewhat. So we change the design and maybe. So maybe we don't have all these individual elements here. Or, yes, hang on, is an idea. We make this into a circuit board. We'll give it a conformal coating, so it's waterproof. Both sides, plenty of lacquer conformal coating. Make it into a circuit board. Feed. I like the idea. I'm liking the idea of this now. Circuit board, yeah. So basically, we have relays on here, and all the wires come back to a point, but they can be then switched to the feed point or not. Either switch to the feed point, or so that the normally closed relay switches it to the feed point, all of them by default. Then you can switch, when you switch them on the relay, it disconnects being fed to the feed point and switches it over to which, yeah. So you'd have to have your switching would have to be, see, multiple switching relays. So yeah, so we'd switch off that connection and join it to one of the other cables that going up onto this one. So we'd have to write a table, a lookup table, and write a little program, little C++ Arduino ESP32 type of program, and we'll switch in. We'll have to do a circuit, so we could design a circuit for that. So basically this plate will turn into a circuit board that takes the feed plus 12 volt DC fed from a 2-core cable, or do we do RS485 wireless? Could switch it wirelessly. Let's have it wireless. Is that going to interfere with anything though? Wireless. Need to do a few tests. Probably be, well, there's wireless all around the house anyway, so it's probably going to be fine. But when it's close to the antenna, do you want Wi-Fi signal close to your antenna? We could try it. If not, we could take it remote and do an RS485 connection or something down a 2-core cable. So tell you what, should we take the background off? Let's take the background off a minute. House, have I got the relay? Hang on, let me just find out if that's Right, there's no layer on there, the rest of it. So let's garage. Garage, we can get rid of fence. Shed. Can we get rid of any of this? This is all, yes, none of that's. I think we'll leave that there. Shall we leave that there? No, let's get rid of it. Right, okay, select it, group it, and we're going to put it in. I'll put it in with a house layer. That's it. So I've just got now the antenna and the hex beam. Can we get rid of the antenna for a bit? Yeah, we could do, because we don't need that at the minute. So let's get rid of the antenna. Rails. Oh, keep the bolts. Choke. I'll leave the choke. Alright, mounting pole. Plate. Radial. Spider hub. Fixing the stays. So we've got nothing else there. We want rid of this pole, don't we? What is that? Layer 0. Let's call it under antenna. Right, okay. So now we've just got the web. The cobweb. Okay. So what about if this is a circuit board? I'm liking the idea of this. So then we could... what about... Here's another idea. It is a think tank, after all. It is a think tank. Right, so what about if we were able to switch sections together? And what you could even do this, you could even feed around there, back round, and you could keep doing this all the way around back again. Right, and there's that way, and then you could switch individual ones. So we need a way of switching in different wires. Now what about, so if it was a hex beam, this would be your direction here, your beaming direction. So what about if we could switch out different sections altogether? So you switch out directions, and you don't need a rotator then. You wouldn't need a rotator. So you imagine you got that there. In fact, I could simulate this, couldn't I? Yeah. Let's tell you what we'll do. I'll come on to there. Oops. Why is it doing that? Oh, wrong thing. Right, hang on. So if we used to switch, if we was to do that, maybe can we? Oh, we have to break onto it. So imagine, I can't do it by selecting. Why not? So imagine if it's beaming towards me, then we switch in a different section. So we could beam this way. We could swap beam to there, then there. So you've got a directional rotator, but in the hex. Yeah. So In order to switch out whole sections, you've got to have the ability to disconnect and connect all these wires. Every joint on it needs to be able to switched in and switched out. Right, I've got to go for an interim second, so I'll back in a second. Hello, we're back. Right, so what have we got? Got plenty of ideas. Lot of ideas. So to switch individual sections in and out. So we've got 2 joints. Now you'd have to have the relay out here. For an antenna, you'd have to do the switching. If you wanted to switch this from there over to this one, you'd have to switch it there, because you can't have the circuit board all on here, so you'd be taking that back round then coming up again, so you wouldn't really be switching it round there. But you could be switching it. But then again, if the cables are running in parallel next to each other, it'll be adding to the length, but the RF, the resonant type of stuff, the F, would not necessarily travel down there. It'll travel up, it'll find the link, but it can't find the link. Don't know, it's a weird one. So it can have to be very experimental. So we can't have relays here and there everywhere. It's got to be in one place. So it's going to have to be this hex plate. It's going to have to be a circuit board. It's going to be developed into a circuit board with relays around it. Now these are catenary wires, non-conducting catenary wires at the minute. So, yeah, you could go on so many tangents. You've got to be careful. You stick to something. So I think to keep it from exponentially growing, unmanageable, too much workload, impossible to complete, we'll narrow the expectations a bit. So I think what we want to do, we want to be able to turn this 20 meter, so that if we lose all this, if we just send 20 meter down it, and it goes down the resonant frequent route for 20 meters, you lost all this. All this will be redundant, maybe. So what we do then, instead of making it redundant, we switch. If we want to do 40 meters, we go down, go round and down the other one. But that gives us 15. So you've got 20, 15, 12, 10. 6 and 4 meters. So 6 and 4 gives us 10. So effectively, if you were doing switching, you wouldn't need so much of this. So we got 4, 6 and 10. That gives us 20 meters of length. If we switch all those 3 in, plus we'll have the length that comes back. So this is going to be adjustable depending. Switch from this end, so you've got to allow for this bit in with your 4 meters, from there to there for your 6 meters, from this feed point over to there, around and back to that shield or feed point for your 10 meters. So that will give us our 20 meters, and we know this last one is 20 meters on its own. So if you could feed to your 10 during these two, so if you switch them in, you've got 20 there and 20 there, 40 meters maybe. Yeah. So what else have you got? So you got your 10 meters there, so then you got your 12 meters. So you got 12 meters and 15 and 20. So 12. Yeah, there's so many different combinations here. I'd have to draw a table to work out how many different combinations. So, in order to design this, the circuit board with all the relays switching on it, you've got to determine. I suppose you ought to have the ability to switch everything. Let's count it up. So we need to be able to switch this one here. Switch that. Switch that. So 1, 2, 3, 4, 5. 5. I suppose we could have 12 relays, or 12 relays. Yeah, 6 on each side. Switching these elements in and out of one another, but they always, without power, they're all engaged. Yeah, without power they're all, so you've got your normally closed circuit without energized relays. They're all wired to the feed point of the screen, which give you your standard Cobweb X, and the resonant frequency will automatically find its own, even though they're all connected. Then there's a way of energizing the relay to whichever one to switch it through to another one. Yeah. So what we've got to derive a way. So you might want to switch this one onto this one over here, or any combination to get in between bands and stuff. So so each one would have to have, each band would have to have 6 relays. That's a lot of relays. Too many relays. Too many relays. So you'd have to work out. I suppose you could make it with switches to start with. A bit like programming a microcontroller. Bits, you'd have your bit reference, basically. So, be nice to be able to switch any combination together. You could do it like a rotary channel select, or a addressable something or other that switches, microcontroller that switch the relays in and out to a bit pattern. Yeah. So we start from there, we go around, and we come back by default on all of them. And then if you want to switch to the next band, so actually you only need to switch one side, don't you? Is that right? No, because if we want to go from here round and then switch round to there, then out to there. So it's every other one. Probably don't need the same switch cable, so one will be fixed. So we know that's going to be fixed to there. That goes round, so we start fixed, so you can't adjust that side. Go around. Now that would default back without being switched, and then if you switch it, it switches over to this one. Then that one, so it switches over to this one here, and that will be fixed. So that's fixed going back to there. But if you switch this one on, which means you're trying to send the signal this way, so you'd have to break the signal going back that way. Yeah. So you break the signal going back that way, and you'd bring, and as you switch this one in, it breaks. So this on a double pole changeover relay, it would switch this one from there to there, but also the second RLA B would switch, disconnect this one going back, and then connect that one. Well, no, it just needs to disconnect that one, doesn't it? You don't know whether you wanted to connect that to the next area or not yet. So we'll have a single change rate, single pole change, single pole changeover contact. Defaults to feeding that straight back to that feed point. Energized, it feeds it up, it joins that one with this green. And then you'd have another contact the same. So you could do experimental one with switches, but I mean, so then that would go round here over to this one, and that could either go straight back then or be switched to this one. I'm liking this idea. So another single pole changeover switch there. They'd have to be independently energized, so you could got control. If that was tied in with this one, for instance, you'd be switching both out at the same time. You won't be able to control the direction. So let's suppose we start from here. We're going round. No, start from here. We go up here with the orange, back to there. Then we decide we want to add the 4 meter and the 6 meter together to give us 10 meters. So then we switch over the relay. It then connects to here and it goes back down, round here, and then back, and that'll give us. So that needs to be switchable. Then you want to single pole chamber, switch it over to join them two up. So every one of these needs to be a single pole relay or switch. Single pole changeover. So the center, the common would be connected to the, the common would be connected to the element, and normally closed would be connected to the feed line. Normally open would be connected to the next band. So if you wanted to do something wild, like go from there round to there, 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 and back again, and all the way back, it's possible to do it with switches. So single pole changeover. Now the last band you wouldn't need to. Would you want? You'd need a relay there to energize it, to disconnect it, but then you'd still have that bit connected there. So would it matter? So always the last band, or the outermost, is always connected, so you have to utilize that. But what if you don't want it and you want to come down here? Well, it doesn't matter, because then it'll be resonant. It'll automatically pick out the resonant band anyway. So at the minute we'd have a relay, single pole relay there, single pole changeover, single pole, single pole, single pole, single pole. So you're looking at 1, 2, 3, 4, 5, say 10 maybe, plus another 10. So this would have to be capable of 20 relays probably, or even 22 relays. Right, so a circuit board wise, you could easily create it in a circuit board. You'll have to use some small relays and conformal coat it, spray it with conformal coating after, and then the PCB would be the You could change these for each one of these is fixed down to the terminal, or through a strain relief and then to a terminal that goes into the relay. Then you'd need some way of switching this remotely. I could use one of my microcontrollers. So use a microcontroller to switch it. Okay. So there's that idea. What do we call that idea? We're going to call that sort of like an antenna tuner, but without doing it with wire instead of capacitance. So as it stands, as it is with no switching, the resonant frequency will automatically go down the right element. You've got your 4, 6, 10, 12, 15 and 20 meter bands, and then you can utilize, with a bit of switching, you can turn your 4, 6 and 10 into another 20 meter to give you the outermost one, and these three would give you your 40 meter band. Now what else could you do if you carried on? So you got your 12 meters, 15, no, 15, 12, and yeah, 15 and 12. So that's another, yeah, it's weird. So you got your 20 meter, another 20 meters, and then you got 15 and 12. So what about if you add an extra band? I don't know, this is weird. Very strange, lots. It's all experimental. Very experimental and crazy. But we've got the ability to switch stuff. I can switch stuff. I've got all the infrastructure in place, the protocols for programming, a microcontroller to switch stuff. Right, so that's an antenna in its own right. Then what about a tuned ground plane then for the... So the same thing would apply to a tuned ground plane. So then you need to switch the feed, the center feed, from vertical antenna to horizontal web. So we can start from here. They say this is a screen side. We go around our 4 meters and back again to the center core. So if we was to switch that out from there over to the vertical, or would you just short it out, join the two together? Probably join the two together. So let's put the antenna back on. Right, might as well have the pole. The radials. Do you need radials? These are the radials. Right, let's put the radials on. Where are they? There's the 10 meter radials. Right. So the only thing I don't like about this is the vertical's not centre over there. That's the only thing I don't like about it, but there's not much I can do about that, the physical thing. Unless there's a way of offsetting this. Couldn't really offset it, could you? Anyway. Right, it's a weird one. Let's put all the stuff back in. Let's put the shed back, and let's put everything back in. Let's just tick it all. Let's find out what to do. Tick it all back on again. Right, so we've got our house back. We've got any rogue stuff anywhere? Did we lose this? Catenary choke, bolts. Right. So. Yeah. So today we're coming up with some ideas. This is Hex Cobweb, Hustler 5, BTV, ground plane, think tank ideas. So we've got our 6 catenary wires to fasten our Hex Cobweb to, which are screwed to the fence or wall with a bungee and an insulator, although it's non-conductive wire anyway, but anyway we need to join it somehow neatly, so yeah, there's that. Okay, we join to the wall, the fence, the brick, all around, wherever we can. So let's see what it's like if you stood in the garden. So you stood in the garden, you're walking around the garden. Oops, lost it. Let's come at this angle. Let's go into there, that's it. So I'm stood underneath. I'm in the fence. Right, let's just go across a bit. I'm sat in my garden, looking out at the sky. The garden fence is cutting me head off. Right, so this is what you walk around. This is what you can see. Oops, sort of. It's difficult. What about if we go X-ray? X-ray. That's all right. So if we can see X-ray. Oh God. See through. Yeah, X-ray is good. Right. Wireframe. Let's try wireframe. Turn off X-ray. Okay, so we've got wireframe. Not very good. Don't like wireframe. Oh, let's get rid of the X-ray. Right. What's this one? Style, edges, depth, Q, extent. I've never tried any of this actually. Back edges, edges. I'll leave that alone. Right, so what do we do now? We've designed some kind of switching system. So we want a circuit board made. How big does the circuit board have to be? Let's measure it. So 200mm by 200mm circuit board. It'd have to have relays on it, sprayed with a conformal coating so it's weatherproof. And you'd have to be able to put these wires into terminals, these elements, into a strain relief, and then over to terminals. I've lost my cap. Where's my cap gone? Thought I made a cap for that. Oh well. Right. Yeah, so it is very experimental. So we couldn't have a relay here. What about if these were circuit boards? Here's an idea for you. Here's a new idea. We like ideas because We're a think tank. No, we're not. We want to be a think tank. We're full of ideas. So here's an idea. What about if these were circuit boards? If these were circuit boards shaped, they were also a locking stay, but also a circuit board. And you wire your element to the circuit board, and it's got its own relay on, and its own 12 volt supply. So there's a 12 volt supply. It comes with terminals, 12 volt supply, relay, and it's addressable. It works on a 2-wire addressable, like an RS4 or a CAN bus, and it's capable of switching to the next, the one, so you'd have to feed in and feed out. Feed in, feed out, and it'll either feed it straight back to the previous one, which could also feed it straight back down, or switch it and feed up. So yeah, you could make this into a circuit board. So your catenary wire, the only thing is your feed for your power would maybe interfere with the antenna. Maybe. Yeah, yeah, maybe it would interfere. That's why we got using not wire but non-conductive catenary. So how about if there was a feed, 2-wire feed, so it starts life over here, 2-wire feed to the nearest switch, which is also a locking stay, and then feeds to another 2-wire to this, but then you'd need the element still, so it would be 2-wire and an element. Now you get RF, you probably get RF going down your DC, your supply. So what about, you couldn't put a PP3 battery in it because that would go flat quick and the weight would be too much on each one, so it'd have to get fed. How do you transfer power? Unless you could make your wire transfer part of the element. No, you couldn't do that because you'd be getting DC down your down to your radio. So there needs to be a separate wire for that. So somehow it would have to be screened off from your element wire. How would you do that? How would you screen your wire off? So you could run a coax, I suppose, a screen coax to feed the power. Now coax, or a twisted pair, maybe. Cat5 twisted pair. Say the two of the twisted pair out of a Cat5 cable that feeds the power. They're lightweight as well, without the sheath. It'd be lightweight, so you could feed a twisted pair to there, twisted pair out on the output to the input, output to the input, and so on and so forth. You need a relay capable of switching the amount of current that you'd require on 100 watts, say for instance. Or you could build it with a toggle switch or a jumper for experimental reasons. But then we spoke about switching the directional side, so if it carried on this wire going all the way around, no, that was going to, we ruled that out because that was going to make it very complicated. At this, we want to keep it as simple as possible. So we make a circuit board? Do we make that stay into a circuit board with a relay on it? And that to be addressable. You'd have to use a little AT Tiny 85 or something. A little 8-pin microcontroller running at low megahertz, maybe 8 megahertz, 1 megahertz, something like that. Would need to be fast just to receive a bus signal or serial command. You'd need to switch from, you'd have input, 2 wires. So what you need the element switching through, then you need the ground and the DC wire or twisted pair. Oh, somebody's got some sick stuff going on. Broadband spectrum of noise. Someone playing Silly Book or something. Right. So they could mill out the circuit board to do the same thing here, or keep it as it is. Anyway, I think let's take it in stages. It's just think tanking after all. Think tank. So I think what we should do is try this as it is first. Get this tuned in. And possibly think about making these switchable somehow, whether they're PCB with an AT Tiny microcontroller on each one, just so you could remote control switch it into any format. But then if you're going to go to all that trouble, why not just make a mag loop? Just make a mag loop and have the tuner remote controllable. Yeah, there's lots of ways of doing it. But for space as a premium, you could get 40 meters out of this. You could probably get 85 meters. Well, you can work it out. Let's get a calculator. Why is that pulsing? So let's get a calculator. Let's work out what we've got here. Let's have a look. So we know we've got our 4 meters. We've got our 6 meters. We've got our 10 meters. We've got our 12 meters. We've got our 15 meters, and we've got our 20 meters. 67 meters. 67 meters. So So we want to. So let's go clear 80 meters. Minus 67 meters. Right. 80 meters minus 67. 13 meters. So we need another. We need 12 meters. I'm just thinking if we could have one more band in between. So 30, we need to make another 13 meters. So that's 15, that's 12, 10, 20. So 15, that's going to be too much. 12 is not quite enough. But some of these frequencies, they're not quite 12, are they? The centre frequency where they're tuned is slightly off. It's more, so yeah. So possibly you could do it. You could probably do it. Experimental. So by adding another 12 meters. So we've got 4, 6, 10, 12, 15 and 20. I think we need another band here. Let's have a look on here. 1.8, 3.5, 5, 7. Which, these are 3 megahertz, aren't they? So we've got our 40. Right, there's one called 10. There's a band on 10 megahertz. 10 megahertz, right, then you got 20 meters. Oh no, that 10. Oh, that must be 15. So confusing when you got different numbers. Right, 10 megahertz. 14. So 14's 20. 7's 40. Right, so there's just a funny megahertz in between, band in between. 18 megahertz. 21. 24 point. So we've got, how many bands we got there? We've got a 50 and a 70. Oh, that's 4 and 6 meters. 10. And we've got 12. And we've got 21, which is 15. 18 is no, hang on. 21. I got confused. I need to look up chart. Let's see if I can find a lookup chart. Let's see if we can find a lookup chart. Alright, so you want megahertz to meters, or meters, no, megahertz to meters. Convert megahertz to wavelength in meters. Right, so 21 14 meters. Alright. What do we got? So 10 megahertz, 29. Hey? What's gone wrong here? What am I looking at here? 28. 28. 10 meters, yeah. So we've got 28. 24.5. 24.5. 12 meters. Right, we've got 21. 14 meters. Right. And we've got 18. 16 meters. So there's a few there in between us. 14 is a 20. So they're not quite 20, they're 21 point something, yeah. So we've got 5 5 megahertz, 60 meters. Oops, I've actually switched band there. HF's a bit rubbish tonight. It's dead, isn't it? Yeah, so there's some opportunities there, so the sizes aren't exacting. Right. What they should do is just give the handbands.
Yeah, you're 5, 9, 10, not 5 and 8. Yeah, very strong, really, very, very strong. You too, over. 73, good night. This is Delta, kilowatt 7, Lima, Japan. Secure DX.
Right, it's basically there. Okay, so we've got 3.5, yeah. So there's a wide spectrum. So the middle of the bands, we want the middle sizes really. The middle of the band. Security X. So 10, 12, 15. They haven't got the 6 and 4 meter bands there for some reason. 2, 3, 4, 5, 6, 7. 30 meters, right? Yeah, that's 10 meters. Yeah, 30 meters. So 30. So we could put one more section in here on the model. That's our 20 meter. We could put our 30 meter in there, which will give us 30 meters, right? So we've got. Let's add them all up. 30, 20, 17. Let's get the calculator again.
Victor Kilo 5 X-ray question mark. Go ahead.
Right, let's add some up. So we've got 30 meters plus 20 meters plus 17 meters plus 15 meters plus 12 meters plus 10 meters. 104, okay. Plus 6 meters plus 4 meters. 114 meters. 114. So, say plus 40 meters. What's that give us? 154.
Roger.
I suppose with all the odd bits that we haven't allowed for, it might give us 160 meters. So there's a reason for all this.
You're about 4 by 4 QSB. 4 by 4 QSB. My name is Per. Papa Echo Romeo. Papa Echo Romeo. 6 Kilo 5 X-ray Zulu Echo. Delta Kilowatt 7 Lima, Japan. Over.
He's a strong signal. Where he's from. Let's have a look. Let's have a look. What was his call sign? Come back, mate. Come back. Do again.
Okay, very fine, Joe. Thank you very much for the 5 and 9 from your side. I wonder, for many years I never understood.
Sound German.
Your country. And yesterday there was one, and the day before too. So this will be very nice.
7.154
Working condition here is about a kilowatt.
Oh, kilowatt.
And full size beam about 30 meters up, looking your side. 6 Kilo 5 X-ray Zulu Echo. Delta Delta Kilo 7 Lima Juliet, over.
Delta Kilo 7. I've lost it. It's got 1,000 watts going. You could bounce off the moon or anything. Bounce off whatever you want with 1,000 watts. Delta Kilo, so yeah.
QSL 70 watts and Delta loop antenna your side. Very fine. My KDH is Kilo India Echo north of Germany.
Oh, Kiel, Germany.
About 100 kilometers north of Hamburg.
Right.
So thank you so much. And
That's what 1,000 watts will get you.
yeah, so we'll get up.
Anyway, so what is going on? So we've got some options here. So where do I go from here? I'll just build this as it is. I'll wire and tune them, make sure this system works. And maybe version 2, if this system works, maybe version 2 will be, these stays will be made out of circuit boards with switchable ins and outs. It's the same one, addressable. Not sure whether the power, I'll tell you what I'll do. We'll set this up, we'll get it all swared in, tuned in as best we can. Then I'll add some DC down it. I'll put a bulb on the end here or something, and 12 volt. Send some DC down to core. See if it affects the tuning. Try to see if it affects the tuning somewhat. If it does, I might have to rethink that. If it doesn't affect it too much, or if different kinds of cable, screen cable, twisted pair, something like that. Maybe some balance ferrites to prevent the RF going down it, or from the DC affecting what would have been the antenna, unless we can make the power feed part of the antenna. I'm not sure if that's even a good idea or not. Probably not. So anyway, we'll start by tuning. We'll tune this up. Fit this. So the catenary wires fit around your house wall and your fence, brick shed. And we'll try and tune it up. I'll look at ideas of switching these segments. Rather than have a rotator, if it's a beam, if it's directional, it's not so much directional, this flat one, but if it turns out to be directional, it'd be nice to be able to switch these segments in and out, so that you'd have this all the way around, but they won't be active, they'll be switched out. So you switch out, so you're basically shorting them out or switching them out of circuit, so you can switch directions. You go this way, that way, that way, that way, this way, or that way. Then no need for a rotator. Obviously the resolution won't be as good as a rotator. I need to do some experiments, so what we'll do, I can't, once this catenary is connected, I can't rotate this, it's fixed. So the alternative is to rotate it electrically, via switching. Anyway, let me think. Anything else we could think of? So we can use switch it as a ground plane, yeah. So it's going to use the vertical piece, so I'll probably connect that. That will be your braid. This will be your centre feed. And we'll need a link. We'll get this high enough to feed up to the centre feed of this vertical. So a bit like a. These will act like shorted rings or coils. So it'll be short. The wire will take it to the feed. It'll go around there and back to the ground, back to this braid. So it's like having a ring, like a, you know, the old CB antennas, comment ringos. Remember them? Let's see if we can find a comment ringo. There we go. Comment ringo. Comment antenna. Yeah, something like. I remember experimenting one when I was about 15, 16. Someone gave me an old antenna. And yeah, something like. Well, it was a square one. It was a square ring. And it shorted the inner and the braid. It shorted the ground or the out through this ring. Is that all we got? No, it's not there, is it? We haven't got the square ones anymore. Square. Yeah, see, that's doing something similar there. See, the short in the centre out through this ring. But all it was literally a square piece of flat that goes round and join the one to the other. Can't see it. Anyway, so basically by joining that feed up to the centre point of this vertical, this hustler, this would act as your DC short, which also would make it quiet, similar to a K40 antenna. Those were quiet. Those K40 antennas were very quiet. Something to do with a DC short. Tell you what, let's bring up ChatGPT and see if we can ask it a few questions. Right, let's see if we can get in there without too much trouble. Right, okay. Let's do a bit of think tanking with ChatGPT now. Alright, so you're gonna let me type? Yeah. Okay, so right, antenna, a DC short. What do you know about DC shorts? An antenna DC short refers to an antenna design where the radiating element is electrically connected to the ground at DC, direct current. Right, so but it can still effectively radiate at the desired operating frequency. This is a common feature in many antenna types and serves several practical purposes. Key concepts: DC short versus an RF operation. At DC 0 Hz, the antenna appears as a short circuit because its structure connects directly to ground. Yeah. At radio frequency RF, due to reactive impedance, inductance, or capacitance, the antenna can still resonate and radiate efficiently. Designs with DC shorts. Shorted monopole antennas. These have a direct connection to the ground plane for DC, but a matching network allows RF operation. Microstrip patch antennas with shorting pins. Don't know what that is. Loop antennas. Loop antenna. The loop structure is often DC short, but resonates at certain frequencies. PIFA, planar inverted F antenna, frequently used in mobile devices. The antenna often includes a DC short for mechanical stability and to avoid static build-up. Yeah, they're going back to DC short for the noise. That's why those K40s were very quiet. Brilliant antenna. I had one for a while years ago. Right, advantages of a DC short.
Kirk,
Alright.
you know that Dave, you know, Rob's dad.
Hang on, I'm on here. Hang on a second. Back onto it. Advantages of a DC short. Static discharge protection. Prevents the build-up of static electricity by providing a direct path to ground. I'm liking that idea. Improved robustness. Offers better protection against electrical surges. Simpler grounding. Simplifies mechanical and electrical integration with grounded systems. Applications: mobile devices, automotive antennas, base station or the RF systems where static protection is essential. Example circuit behavior. If you measure the resistance of such an antenna using a multimeter, you'll see a close to a 0 ohm because of the DC short. However, its RF impedance measured with a network analyzer would typically show resonance at the designed operating frequencies. Challenges: matching the antenna impedance can be complex due to the low DC resistance. Requires precise tuning to ensure desired performance at RF frequencies. If you're working with an antenna as a DC short, it's essential to understand the interplay of DC and RF behavior that impacts both the design and the testing process. Right, I have designed a cross between a hex beam and a cobweb antenna with 6 bands, which are 4 meters, 6 meters, 10 meters, 12, 10 meters, 12 meters, 15 meters, 20 meters. Right. Can you suggest ways to connect these bands together. Ways to connect them together to extend the band coverage to include 40 meters, 80 meters, 60 meters, 80 meters, and another 60 meters. Extending the frequency coverage of your antenna design to include bands requires a careful consideration to maintain performance across all bands. Here are some possible approaches to add these lower frequency bands while minimizing interference with your. Add loaded dipoles for low bands. Install shortened dipoles. No. Implementation. Use inductive loading and capacity. No. Position. No. Advanced. Use traps to integrate low bands. No. Create folded extensions or add radial-like wires. Added folded wires. Right. Implementation. Add a coupled loop or cage structure for low bands. Employ an additional vertical or inverted L for low bands. That's an idea. Could use the. We've already got the 80 meters on the Hustler vertical. Description. Add a vertical. Right. Decouples low band operation from resistance system. Use a fan dipole approach for low bands. Install remote tuners or frequency specific feed lines. Chips for integration. How about if I switch the non-resonant frequency band wires to connect in series with the desired band. To extend the physical length of the wire elements. Using non-resonant frequency wires in series to extend the physical length of the wire elements for a lower frequency is an innovative and feasible approach. This method effectively increases the electrical length of the antenna for the desired lower bands while keeping the design compact. Here's a breakdown of how you can implement and optimize this approach. Key concept. Non-resonant wires in series. When the antenna operates on a lower frequency, e.g. 40 meters, 60, 80, 160, the wires designed for higher frequencies, non-resonant at the lower band, can be switched into circuit. These wires act as extensions, increasing the overall effective length of the antenna elements. Yeah, that's what I was thinking. Implementation, switching mechanism. Relay switching. Use RF related relays to connect or disconnect the non-resonant wires to the desired band wires. Place relays at the key points where higher frequency elements terminate, allowing them to be added to the lower frequency elements as needed. Mechanical switches for simpler setups or where relays aren't ideal. Use manually operated switches at void points. Pin diodes. In advanced systems, pin diodes can provide electronic switching controlled remotely, eliminating the need for mechanical parts. Pin diode? Right, don't know what that is. Feed point configuration. Ensure the feed point can handle the combined electrical lengths when switching occurs. Right. Use a broadband or a band-specific impedance matching network to optimize performance after reconfiguration. Number 3. Example for a hybrid Hex Cobweb design. 40 meter extension. Combine the 20 meter and the 15 meter wires in series for the 40 meter band. Use relay switches at the end of the 20 meter wires to connect them to the 50 meter wire when operating on 40. 60 meter extent. Series connect the 12 meter wires and the 10 meter wires, possibly with added inductance to fine-tune resonance. 80 meter extension. Use 20 meter and 50 meter wires, possibly adding loading coils or capacitive hats to further lengthen the effective electrical path. 160 meter extension. Combine multiple wires, 20, 15 and 10 in series with additional inductive or yeah, it's cheating basically. For benefits. Compact design. Efficient use of existing elements reduces the need for extra wires or space. Dynamic band coverage. Switching allows the antenna to adapt to multiple frequency ranges. Improved efficiency. Longer elements can improve radiation efficiency on lower bands compared to purely loaded designs. Yeah, I was guessing that it would be better than loading coils. Challenges and mitigation. Coupling and interaction. Non-resonant wires may still interact with active elements. Minimize interaction by spacing wires optimally. Using proper switching techniques to fully isolate inactive wires. Complexity. Switching systems add complexity simply by grouping wires into modular segments. Use pre-tuned components for fast configuration. Impedance matching. Series combinations may change impedance significantly. Use a tuner or matching network as a feed point at the feed point for fine tuning. Mechanical considerations. Ensure the added series connections and switching mechanisms do not compromise the structural integrity of the antenna. Tools and testing. Use antenna modeling software, e.g. EZ and NEC, Mamana GAL or 4 NEC2 to simulate the extended wire lengths and predict performance. Right, we'll have to try that someday. Measure and adjust the antenna using an antenna analyzer to do that. I've got nano VNA. Example switching diagram. Imagine a scenario for the 40 meter band. Normal operation. 20 meter and 50 meter wires are used independently for the respective bands. 40 meter mode. A relay closes the circuit to connect the end of the 20 meter wire to the 50 meter wire, forming a single longer element for 40 meter operation. This method is a smart smart way to extend the capability of your hybrid antenna without significantly increasing its physical size. Let me know if you'd like help with specific wiring diagrams, switching setups, or matching network design. Right. Dropped frames, 2.2%. I've got a few dropped frames at the minute. Oh well. Right, so is there anything I need to ask it? Oh yeah. If I have a circuit board at every hex direction change that has a relay on it Right, so if I have a circuit board, every hex direction change that has a relay on it, and the relay is fed, and the relay PCB is fed from 12 volts DC and the power wires run along with the elements I am worried about the DC wires, DC wiring affecting the antenna see what that says. You're absolutely correct to be concerned about the DC wire running alongside the antenna element, as it could influence the antenna's radiation pattern, impedance and performance. To minimize or eliminate these effects, you can adopt several strategies for isolating or mitigating the impact of the DC wiring on the antenna system. Key concerns with DC wiring near antenna elements. Coupling and interaction. The DC wires may act as parasitic elements, especially at high frequencies, altering the antenna's radiation pattern. RF interference. RF currents could couple into the DC wiring, leading to unwanted noise or even detuning the antenna. Radiation or common mode currents. The DC wiring could unintentionally radiate RF energy, creating interference or signal loss. Mitigation strategies. Use chokes to isolate the DC wiring. Ferrite beads or clamp on ferrites. Place ferrite beads on the DC power lines at intervals to suppress RF currents. Select ferrites with high impedance at the operating frequency range of your antenna. Coiled chokes Create a choke by winding the DC wire into several turns around a ferrite core near each relay PCB. Okay. I've actually got some of these little things. I've got some of these pre-wound things that solder to circuit boards. Maybe that could be included on the power feed. This prevents RF from travelling along the DC wire.
November. So they was talking to the farmer and he was talking about the...
Use shielding DC wiring. Shielded cable. Replace unshielded DC wires with shielded twisted pair or coax cable. I was saying the same thing earlier. Connect the shield to the antenna's ground system at one point, preferably at the power source end. Advantages: prevents the DC wires from acting as radiating elements, minimises coupling with the antenna, decouple DC wiring at relay boards, bypass capacitors. Install bypass capacitors at 0.01 microfarad or 0.1 microfarad ceramic across the power and the ground pins of each relay board. These capacitors will shunt any RF energy on the DC wires to ground. Okay. Inductive decoupling. Add small RF chokes in series with the DC wiring before it connects to the relay. Right. Number 4. Run DC wiring orthogonal to the elements. Orthogonal. What the hell is that? Shit. Minimize parallel runs. Yeah, that's going to be a problem. Arrange the DC wiring to cross the antenna elements at right angles rather than running parallel to them. This reduces coupling. Right, that might be an option. Centralized routing. Route the DC wires along the boom or central point away from the elements to reduce their influence. Use a common grounding scheme. Ensure the DC wiring shares a common ground with the antenna system, preventing floating ground loops that could radiate RF. Okay, so ground everything, yeah. Apart from the plus. Remote DC isolation with the RF switching. Right. Bias T solutions. Use a bias T at the feed point to inject DC into the coax feed line, allowing the same cable to deliver RF. I thought about that as well earlier on. Same cable to deliver RF and DC power, right? Yeah. I wouldn't want that to go into my radio though. At each end, at each relay PCB, use a bias T to extract DC power for the relay. Advantages. Advantage: eliminate separate DC wiring, drastically reducing coupling and interference risks. Right, okay. They do something similar on camera systems with old coax years ago. So DC isolation with a bias T solution. I have to look into that bit. Employ low current relays. Reduce the power requirements of the relays by using low current, efficient designs. This allows for smaller DC wires, further reducing their impact on the antenna. Testing for DC wiring effects. After implementation, test for any impact of the DC wiring. Analyze the SWR. Check for changes in SWR with DC power on and off. Field strength measurement. Measure radiation patterns to detect distortions. RF interference testing. Use a spectrum analyzer to identify any RF noise from the DC wiring. Practical example, running DC wires along elements. If your antenna operates on multiple bands, twist the DC wires. Twisting the power and ground wires together reduces their susceptibility to RF coupling. Decouple at each relay PCB. Yeah. Add a bypass capacitor and ferrites near the relays. Centralized DC power distribution. Run a main DC feed line along the boom and branch off at each PCB using short shielded wires. Alternative approach, wireless relay control. Right. For an advanced design, consider using wireless control relays or RF based control system. Use a small wireless receiver module at each PCB. The DC wiring for the receiver is minimal and localized to the PCB. Centralize control via a wireless transmitter. Oh yeah. Okay. Right, one more question. Would Wi-Fi ESP32 2.4 gigahertz using a command and control protocol to switch the relay PCBs. I know it's going to affect the design. Let's just say design. Using an ESP module operated for Wi-Fi based command and control relay PCBs introduces a potential source of interference, but with careful planning and design it can be managed effectively without negatively affecting your antenna performance. Below is an analysis of the potential challenges and solutions. Right, potential challenges. 2.4 giga interference with antenna performance. The SP32 Wi-Fi module operates at 2.4 gigahertz, which might interact with your antenna's higher bands like 4 meters and 6 meters or other components. The Wi-Fi signals could generate spurious emissions or harmonics that may detune or interfere with your antenna system. Well, yeah, I know. RF noise coupling. The SP32 generates RF noise, especially during Wi-Fi transmission, which could couple into the antenna's elements or feed lines. Yeah. Impact on SWR and radiation pattern. Proximity of the ESP32 module to the antenna elements could alter the resonant behavior of the radiation pattern. Limited range and reliability. Depending on the physical layout of your antenna, the metal structure might block or attenuate the Wi-Fi signals, reducing the readability of the command and control. Solutions and design considerations. Placement of the ESP32 modules. Physically isolate the ESP32 module. Mount the ESP32 modules at points far from the active antenna elements to minimize coupling. For example, position them centrally along the boom or away from the resonant parts of the antenna. Shielding. Enclose the SP32 module in RF shielding cases to suppress emissions. Ensure proper grounding of the shield to the antenna's ground system. Minimize RF noise from the ESP32. Use filtered power supplies. Add LC filters or ferrite beads on the ESP power lines to suppress noise conducted back to the antenna system. Decoupling capacitors. Place capacitors 0.1 microfarad, 0.01 microfarad across ESP32's power pins to reduce high frequency noise. Yeah, of course. Low power Wi-Fi module. Configure the ESP to use minimal power for Wi-Fi communication, reducing RF interference. 3. Communication protocol and frequency management. Use short intermittent commands. Configure the ESP to send short control signals rather than maintaining constant communications. For example, use MQTT HTTP commands to toggle relays and turn off the Wi-Fi module when idle. Channel selection. Avoid Wi-Fi channels near harmonic frequencies of your antenna bands. For example, if the 6 meter is a key band, test to ensure no interference from the selected Wi-Fi channel. Testing for RF interference. Spectrum analysis. Use a spectrum analyzer to measure noise generated by the ESP32 in the antenna's operating bands. SWR testing. Measure the SWR of your antenna with or without the ESP module active to detect any detuning effects. Field testing. Operate the antenna and ESP32 simultaneously. Check for performance degradation. Right. Alternative communication solutions. Use if Wi-Fi causes too much interference or is unreliable. Bluetooth Low Energy (BLE) also supports BLE. Typically generates less interference and operates on lower power than Wi-Fi. Sub-gigahertz RF modules. Use low power sub-gigahertz modules ES433, 868 MHz for control, which are far removed from the antenna's active bands. Wired control. If feasible, run a lightweight control wire for signaling instead of relying on wireless communication. Antenna design adjustments. Chokes on relay power lines. Even with Wi-Fi control, use RF chokes or ferrites on power and control lines to prevent any unintended radiation. Adaptive group grounding. Ensure that all PCB ground planes and shields are well integrated into the antenna's grounding scheme to suppress stray currents. Practical considerations for implementation. Power supply. Provide a stable 3.3 volt, 5 volt DC supply. Ripple or noise on the supply line could exacerbate interference. ESP32 antenna plates. Use an external ESP32 antenna with a coaxial connection to optimize placement away from the critical antenna elements. Protocol or optimization. Reduce the ESP32's transmit power and use acknowledgement-based protocols to ensure commands are reliably executed at low power. Summary. Using the ESP32 with a Wi-Fi for relay control of your antenna system is feasible. Requires proper management of placement, shielding, and interference mitigation. If interference becomes problematic, alternative communication methods like BLE or sub-gigahertz RF modules could be explored. Right. So, yeah. There's lots of different ways of doing it. So what about if you have one ESP32 receiving the protocol mounted away from the antenna, then it sends like an RS485 half duplex 2-wire plus a ground between the two, or I2C would be no good, it'd be too far apart. So yeah, RS485 could work, or CAN bus system, Modbus or CAN bus. A bit like an automobile wiring. So you could use a CAN bus. And I just want a simple microcontroller just to do some switching. Once it's addressed, it receives it's got to be capable of understanding a basic command to switch a relay on, switch it off. Yeah. Right, so there's a lot to it. So let's go back to the model. Here's your model. Right, so what we're going to do next stage is to mount all this equipment with no electronics, just direct bands, direct multiband, get them tuned in, put some DC along it, see if it makes much difference, feed a bulb or something, or feed anything, feed a Wi-Fi module, do some tests, compare with or without. Alright, I think that's going to about do it. What we got, nearly 2 hours. That's going to be long enough. So we need to get to this next stage, finish this off, get these connected, get these brackets mounted and these bungees with the catenary wires, get them all mounted, and get some of these bands tuned up at least with these locking stays, manually adjusting them. So it would be nice if it was like some kind of servo that could move them along. Actually, if that was a circuit board with an input and an output for the elements and a relay to switch backward or forward to the next element, and some way able to move itself up and down, you could introduce automatic tuning and a mesh network, so they could all alter the just self-tune to the right frequency. But then would you need all these others if you could tune? Could you just have one of these hexes that adjusts itself along the catenary? You'd have to have some kind of feed system on a winding recoil system. So your feed line automatically winds in and winds out. That's an idea. On a barrel, a winch. Just needs to be sprung loaded really, so when you pull this out, it takes a bit more feed out. But the fact that it's coiled round would act as a kind of coil anyway. We don't want to put any coils into it, so unless where it coils out, it would have to be bare wire, wouldn't it? If you had a brush kind of system, no, it wouldn't work. Bad weather, corrosion, not a good idea. So it's just, yeah, it's a matter of switching them, I think. Switching them, we can conformal coat the circuit boards, make them waterproof, and they just physically switch between the wires. So yeah, it's slowly going back to a magnetic loop antenna, where you tune it with the, remote tuning. So maybe that's why everyone uses a magnetic loop. Anyway, but I want to use this as a ground plane as well, and an antenna, and I've got all the stuff, so I've got to build it. I think in the future I'm going to be building a magnetic loop antenna, I think. Pretty sure. Maybe out of copper tube. Copper tube, maybe. That'll probably be number 3. So we've done Hustler mods, Hustler plate, radials for 10 meters, raised or elevated. We've done it. Got to do this one next. And I need to do a small 10-minute series on, after all the series of videos, an overview of, a quick overview from start to finish within 10 minutes exactly, and then at the end a summary or a roundup of what we learned. Okay. Anyway, I've got to draw a line there. No pun intended. Draw a line. Don't make me laugh. Anyway, right, let's switch over. So that is gonna be it for today. Did a bit of think tanking and some ideas. It's think tanking and ideas. Joining the Hustler to Cobweb, Hex Cobweb, as a ground plane or an antenna. Some ideas, good ideas there, bad ideas, crazy ideas, not so good ideas. You probably get 10 ideas, and 9 of them are madness. 1 might be brilliant. Anyway, that is gonna be it for today. I'll leave it at that. Thanks for watching, and let's give you a commercial outro. Bye bye. See you soon. Ta-da.